Tonight's lecture, Professor Dave Morrison. Dave is one of the key players in this field of mathematics and physics, and he's one of the people who are responsible for this remarriage of mathematics and physics. He studied in Princeton and Harvard, received his PhD in mathematics, in fact, at Harvard University in 1980, then soon became assistant professor in Princeton, moved on to Duke University, where he became professor of mathematics, and since 2006 he has been a joint professor of mathematics and physics in Santa Barbara. And as I said, Dave is really well known in our community and famous for many seminal contributions, both in mathematics and in physics. In particular, he's one of the two fathers of F-theory, which is a type of string theory, which, as I said, very dramatically and beautifully realizes the link of mathematics and physics. And he is, I would say, one of the few people to whom one can both talk in physics language, which I can confirm since I'm a physicist, and of whom also mathematicians know, since he is a mathematician, that he knows the math really by heart and inside out. So I think he is absolutely predestined to give this talk, and I look very forward, and thank you for teaching us about the math and physics marriage.
Thanks very much. So my topic tonight is the remarriage of pure mathematics and theoretical physics. As a result, I'm going to have to tell you a little bit about pure mathematics in a little bit of detail, but not for very long, don't worry. And a little bit about theoretical physics. It'll be quantum physics. So I hope you might learn a little something about the two fields. But my main story is going to be about history and sociology, how these two communities of researchers diverged and then got back together. And I'll try to tell some of the scientific story that underlies the sociology of what was happening. Yes. Yep. Slide it down. Okay. Okay. So I'm going to begin with a quotation. So this is a quotation from Freeman Dyson, who's one of the originators of what's called quantum electrodynamics, one of the most successful theories in theoretical physics that we have. And in 1972, he was giving a lecture to a group of mathematicians and said the following: as a working physicist, I'm acutely aware of the fact that the marriage between mathematics and physics, which was so enormously fruitful in past centuries, has recently ended in divorce. So that was his take on the situation in 1972. I have another quote from the biographer of Richard Feynman, James Gleick, who wrote a wonderful biography called Genius of Richard Feynman, and describes Feynman's graduate school days, which were between 1939 and 1942. So this notion that the two fields were separating goes back even a little further. I won't read the whole thing, but Gleick points out that pure mathematics had been going in different directions, fields of no direct use to then contemporary physicists, and in fact used some esoteric fields in mathematics, such as the study of shapes in 2, 3, or many dimensions. And as he says as well, an effective divorce had occurred between mathematics and physics. So I want to go back to the first quote just briefly. And what I'll do is explain something about the fruitful collaboration or marriage between mathematics and physics over earlier centuries. I'll explain some of the features which led to this divorce that was happening in the late 30s, early 40s, which Dyson commented upon in 1972. And then we'll go on to describe developments subsequent to this, which actually started to happen not so long after Dyson made this statement, which got them back together. And it's a really fruitful collaboration again, as it had been in earlier times. So the historical collaboration, I'm just going to give some examples. And these examples have both a name and a theory associated to them. And I'm hoping that many of you will have heard these names and or theories. So Isaac Newton, who worked, of course, in the 17th century, quite a while ago, formulated both his famous laws of motion, the first law, second law, third law of motion, and his theory of universal gravitation. It was done in his tremendous treatise. And in order to formulate those things, he had to invent what we now know as calculus. In fact, one of the pleasures of having moved to Santa Barbara and joined the physics department as well as the math department is that I've been asked to teach freshman physics from time to time, whereas in the past I'd only taught freshman calculus from time to time. And what I like to tell my math friends is that I've now taught the other half of Newton. One half of Newton was the calculus. The other half of Newton is the Newtonian mechanics, which is what we teach to freshmen in physics classes. And Newton would have been appalled to think that we had divided the field into two halves. It's really one basic intellectual achievement that you've developed this mathematical tool in order to describe the physical world. The subsequent study of the equations that were generated by Newton's theory occupied mathematicians and physicists in concert. In fact, I'm not sure exactly when to date a division between mathematicians and physicists. There was the term natural philosophy, which was used for a long time. Probably somewhere in the 19th century, people started to specialize enough that you could make a distinction between a mathematician and a theoretical physicist. But clearly, for 200 years or so, people were working on Newton's theory, and they didn't worry too much about which label was associated to them. Another great achievement in theoretical physics, Maxwell's theory of electromagnetism. In order to be formulated, Maxwell had to develop some kind of mathematical theory of this new idea for how electric fields worked, which was that you had something known as a tensor field, which extends throughout space and time. And he had to develop some mathematical tools for doing that. A little bit later, so Maxwell is mid-19th century. Early 20th century, Einstein, of course, first he did the special theory of relativity, which is in many ways, mathematical ways, an extension of Maxwell's theory. But the thing he worked hardest on was the general theory of relativity, which he finished in 1915. And he had to use a very sophisticated mathematical theory known as differential geometry, which, fortunately for him, had already been studied extensively by mathematicians before he needed to use it. It took quite a while to figure out that that was what was required to formulate general relativity. And of course, it has some important physical ideas of its own as well. It's not simply a mathematical construction. And then the final example I want to give is the early development of quantum mechanics. The first ideas of quantum mechanics are due to Werner Heisenberg and Erwin Schrödinger, but they benefited tremendously from the input of mathematicians who began studying the theories that they had produced. In fact, Heisenberg and Schrödinger produced rather different-looking versions of quantum mechanics, and it was really through the help of Hilbert, Weil, and von Neumann that people were able to realize that there was just one theory being proposed describing physical phenomena at the subatomic scale, which is where, or atomic and subatomic scale, which is where quantum effects start to play an important role. So there was a long history of collaboration between mathematicians and physicists. Even as the fields grew to have their own individual identities, the spirit of collaboration was maintained. So I will date this last episode to the 1920s and 1930s, and really the attention of physicists turned to a problem, which I'll get to in a couple of slides, of how would we reconcile quantum mechanics with, first, the special theory of relativity. So that was an important theoretical problem, and people worked on it very hard in the 1930s and 1940s. And in so doing, they diverged from techniques which satisfied mathematicians, and that's one of the causes of the divorce that I'm now telling you about. So I want to mention why mathematicians are very cautious about the use of infinity. This use of infinity is going to show up in a few minutes when we start talking about specifics in this extension of quantum mechanics that is needed. The extension is called quantum field theory. But mathematicians are pretty nervous about infinity, and this is because what we do as mathematicians is we proceed by reasoning logically from some starting point. Many of you in this room, and I prepared that sentence with the knowledge that the average age in the room is close to my age. Many of you in this room will have studied Euclidean geometry in high school. They don't quite do it that way anymore, at least the nice axioms and postulates, and you had to derive the results and so on. The two-column proof with the statement and the reasoning, all that stuff is a little bit gone from the curriculum. They're still doing it somehow, but not quite this way. But it really enforces the notion, going back to the ancient Greeks, back to Euclid's Elements itself, that you could start with some assumptions about the structure of the reasoning system that you're looking at and proceed logically from those minimal assumptions to derive everything else. So that's a real difference between mathematics and physics. In physics, it's the real world which is our guide to the appropriate subjects of study. Mathematics is about how things might fit together and all the possible ways that they would fit together or the possible relationships that they might have among each other. And if you're doing that, you have to be quite careful about putting things together logically, not appealing to an observation of what's happening in nature in the middle to reinforce your intuition about what's happening. So in fact, this axiomatic viewpoint about mathematics was really quite popular in the late 19th and early 20th century. And there was a lot of development, particularly when it came to reasoning about infinity, and some pitfalls were identified in reasoning about infinity. So let me just give you an example. It's easy to conclude that there are as many even whole numbers as there are all whole numbers. So how do we do this? We just write down all the numbers, 1, 2, 3, 4, 5, 6, 7, 8. I stop there. And then we write down all the even numbers, 2, 4, 6, 8. I stop there. And then to each number, we assign the double of that number. So 1 goes to 2, 2 goes to 4, 3 goes to 6. Another way of saying this is that I can take the even numbers, 2, 4, 6, 8, and I can count them using the usual numbers as the counting. So the first even number is 2, the second even number is 4, the third even number is 6, the fourth even number is 8. And you can continue that forever. And it leads to a real puzzle, because what about the odd numbers? Somehow I got the same number of all numbers as the even numbers, but I left out half the numbers in doing so. That demonstrates that we have to be quite careful when we're reasoning about infinity. Things can go wrong pretty easily if we just take our reasoning processes that we're familiar with finite objects or things that can be enumerated with a finite number and extend them to infinite objects. As another example, and we'll come to a case of this in just a few minutes, if you are trying to add up infinite series. So what I mean is I've got some infinite series of numbers, and then I'm going to try to add them all together. And the answer can be ambiguous depending on how you group things. So I put in a lot of parentheses here. I'm sorry about that. But what I'm adding is numbers that go 1, -1, 1, -1, 1, -1. And I put the minus ones in red to help you see them. So the first grouping has first the 1, and then -1, 1, and then -1, 1, and then -1, 1. So what's the answer in that first grouping? It's 1, because I've grouped together all the other intermediate sums are 0. The second grouping, I grouped together the first 1 and -1 pair. So I've got 1 plus -1, 1 plus -1, 1 plus -1. I interrupted in the middle there, but that's part of a 1 plus -1 pair as well. So what's the answer this time? 0. So a mathematician doesn't like this. A problem is supposed to have an answer, right? It's not supposed to have two different answers depending on what you do. So we learn to be very cautious about infinite series. On the other hand, there are some infinite series which are unambiguously divergent. They get large no matter what you do. 1 plus 2 plus 3 plus 4 plus 5. Let me add some of those together for you. The sums are 1, 3, 6, 10, 15, 21, 28, 36, 45, 55, 66, 78. And obviously those numbers are getting larger and larger the more numbers you add together. We use that symbol infinity to indicate that the sum has diverged. It's getting as large as you like if you take enough terms in the series. So So even though we have to be cautious about rearrangements and things of that sort, there are conditions under which we can be assured that some of these infinite sums will converge. I'll get to a convergent one in a moment, and some of them will actually diverge. So here's one more divergent one where it helps to group the numbers again. So this time I'm taking the sums of the reciprocals instead of the sums of the numbers. I told you I'd give you a little math. Here it is. It'll be over soon. If you're getting lost, just hold on. We'll be fine. So here I'm going to group, I'll start out with 1 and then a half, and now I'll group a third and a quarter together. I'll group 1/5 through 1/8 together. I'll group 1/9 through 1/16 together. I'll group 1/17 through 1/32 together. And what I've done is I've grouped the numbers up through 1 over a power of 2. So the last one in the group is the 1 or the 2 or the 4 or the 8. And except for the first term, which is unusual, all of those grouped terms add up to something bigger than a half. So because a third is bigger than a fourth, and I've got 2 quarters, I get a half. Because a fifth, a sixth, a seventh are all bigger than an eighth, and I've got 4 eighths, I get a half. So the next 8 terms give me 8 sixteenths, that's a half. The next 16 terms give me 16 32nds, that's a half. So I get something which is bigger than 1 plus a half 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 plus a half, and that's diverging to infinity. So we can make sense of divergent series. OK, so this is the part that's really scary. We can also do some convergent series. So if you ever remember calculus and Riemann sums, you can look at my diagram and understand what I'm doing. Squared, OK? By a cute little trick, I draw a bunch of rectangles with those areas, and I notice that the red rectangles have an area that's less than the area under the blue curve, starting from 1 going to infinity. And then I have a method from calculus of computing the area under the blue curve, and it turns out to be 1. So I added up this infinite sequence of numbers, and I got something that had to be less than or equal to, actually strictly less than 1. In my diagram, I didn't put the first term, the 1, so the whole sum is less than 2. Turns out that people know what it is. It's pi squared over 6, and that's less than 2, so we're in good shape. OK, end of detailed math for now. We'll come to a little detailed quantum physics later. So in the 1930s and 1940s, as I mentioned before, people wanted to combine Einstein's special relativity and the new theory of quantum mechanics to get something called relativistic quantum field theory. And they succeeded in doing this. But in order to do it, they had to deal with many kinds of infinite quantities. So I want to try to explain why the infinite quantities come up. One of the interesting features, so one of the key features of a quantum theory is that it's inherently probabilistic. Something might happen some percentage of the time, and for example, a whole sample of radioactive, some radioactive element, some fraction of those radioactive atoms are going to decay over the course of the next week. And you know what the fraction is, but you don't know exactly which ones will, because there's some probabilistic effect happening in quantum theories. In quantum field theory, there is a fluctuation, which is, again, due to these probabilities, a fluctuation at subatomic scales of empty space itself. So that sounds a little strange, but once you've realized that there can be these probabilistic effects which tell you that the thing which is the average likelihood to happen is not the only thing that can happen. Other things can happen as well, but with lower probability. You end up with this conclusion when you try to make the quantum ideas relativistic that there have to be these fluctuations at subatomic scales. And the fluctuations have to occur at many different frequencies at the same time. So if you want to understand the effects of the fluctuations, you have to add together effects from each individual frequency, and that's often expressed as an infinite sum. So this is a theory that's built from the ground up in terms of infinite sums, and the physicists who developed the theory have wonderfully accurate ways of evaluating these infinite sums but they are ways that drive mathematicians crazy because we can't start with axioms and manipulate the infinite sums in the way that we would like to do it. We're forced to use this collection of heuristic rules, which are very well justified in terms of producing theories that well describe the universe around us, but don't have a good mathematical foundation. So here is a very common physical picture of an effect from a quantum field theory. And this is called the Casimir Effect. It was observed by a Dutch physicist whose first name I forgot to look up, but his name was Casimir. Most of the people I'm naming, I'm putting first names as well. And what he observed, well, the theoretical setup is shown by this diagram. We've got these fluctuations in the background represented by those green waves. And those fluctuations are interrupted by putting these Casimir plates in the vacuum. So the Casimir plates have to be close enough together that quantum effects are playing a serious role. And for example, we all hear about nanotechnology, and a nanometer is the right scale to put plates together to see this Casimir effect. And so if you want to predict what the effect is going to be using this theory of quantum field theory, you should sum over all of the frequencies, figuring out what the total force is between the plates. So people did this, and the answer, I've left out the units, but the answer that they got is, because I'm summing over all the frequencies, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. Well, we just learned that that's not a really good answer, particularly from a mathematician's point of view. That's going to give an infinite amount of force. The guy actually did the experiment. He put the plates in a vacuum. You have to do some work, right? Because you have to create a vacuum chamber, and you have to be able to stabilize these plates so that there's a parallel space between them, which is very, very small. And then you have to have a way of measuring the force that's induced, but this was all done in the laboratory. And in fact, the theory says that the sum of that series is supposed to be minus 1/12. Really? That's what they say. And you can measure the force. And again, I've left out the units, but it agrees with that value of minus 1/12. So there's something to this, but it's something that makes mathematicians very uncomfortable. In fact, there are ways of forcing the answer minus 1/12 to come out. And just for fun, I'm going to show you one of those ways. There are a number of different ways of doing it, and you can get all sorts of different answers depending on how you choose to do it. The way that I'll do is a way that's often used to justify the answer in quantum field theory. But this was one of two basic causes of the divorce that I mentioned. The first was alluded to in the second quote that I showed you, the one from Feynman's biographer, that explained how the subjects of interest to mathematicians had really diverged from physics and had gone into some more modern things, such as the field called topology, which will recur in this talk a couple times. But then on the other side, mathematicians were very wary about what the physicists were doing. We could see that they were constructing theories that have great agreement with laboratory experiment. And I should say, this is just a tip of the iceberg in terms of experimental agreement. The quantum field theory that was produced by the late 40s and early 50s, called quantum electrodynamics, is reputed to be the most accurate theoretical part of theoretical physics that we have, where you can demonstrate something like 14 or 15 decimal places of agreement between a laboratory measurement and a theoretical calculation, which is just astonishing in terms of its accuracy. But it uses all these weird techniques. So let me just spend another brief minute on some mathematics. We've done the physics of the Casimir effect, so somehow, oddly, quantum mechanics is causing this force. But let me spend just a minute on the mathematics. So we already had series like this. We had the sum of the reciprocals. We had the sum of the squares of the reciprocals. And now I'm going to introduce a variable for that exponent. So I might take cubes of the reciprocals, fourth powers of the reciprocals. And if I did the very strange thing of using s equal minus 1, I hope you remember that a negative exponent means take the reciprocal. So that would just be s equal minus 1 in here would correspond to the sum that we're looking at, 1 plus 2 plus 3 plus 4 plus 5. And the argument that I gave you with those square boxes whose area was adding up to less than the area under the curve shows you that you actually get a nice sum, a nice convergent series, whenever that exponent s in the denominator is bigger than 1. So we did the case s equal 1, and we saw that it diverged. We did the case s equal 2, and we saw that it converged. But in fact, it converges for anything even a little bit more than 1. Now, it's diverging for s equal 1, but it turns out that if you multiply that divergent value for s equal 1 by 0 in the form of s minus 1, you get a nice function, s minus 1 times zeta of s. That's a zeta, by the way. S minus 1 times zeta of s, which approaches 1 as s goes to 1. So that is a nice function of the exponent. So I don't know how to explain how mathematicians ever thought of this idea. This is an idea due to a great 19th century mathematician named Riemann, who's also responsible, by the way, for those boxes. It was another one of his interesting ideas. But you multiply by s minus 1, it approaches 1 as s goes to 1, and now you can use something called power series techniques to figure out what the values are for s bigger than 1 and figure out that those values have to continue in a natural way by using an appropriate power series to values of s less than 1. And in particular, you can identify in this new function extended by the power series techniques a value for zeta of minus 1, and it turns out to be minus 1/12. So there is a way, a sequence of reasonable steps that leads to minus 1/12. But I could have taken a different way of starting on this function and making a sum, and I would have gotten an answer other than minus 1/12. OK, that's the most complicated math you're going to see in this talk. So I arrived back at divorce. And as I said a minute ago, from the mathematician's side, it was that physicists were interested in pursuing these theories which involved things like manipulations of infinities, which didn't involve things that mathematicians were comfortable with. And from the physicist side, the problem was largely that the interests of the mathematical community had, for the most part, departed from the interests of the theoretical physicists. I want to emphasize, yeah, I'll do it later. OK, but shortly thereafter, there was a reconciliation. So in fact, the divorce itself, even though this quote is from 72, as I said before, really dates to the late 30s, early 40s. And the reconciliation happened not so long after Dyson wrote those lines in 1972. And I am going to attribute the reconciliation to two particular problems that arose in theoretical physics, both of them in theoretical particle physics. And these two particular problems, there was some headway made, but it was only after the theoretical physicists got into contact with pure mathematicians, and it was only after they were talking for a while and started to realize that what they were talking about, even though they had developed it separately, had a lot to do with each other, that they started to get together and work side by side. So the first of these problems, I'm only going to devote this paragraph to. I tried to think, how can I present this to this audience, and I just failed. So I'll just tell you a little bit about the story. It's the story of anomalies in quantum field theories. And a quantum theory of a physical system is always associated to a corresponding classical theory of the system. And all that means is a theory that uses Newton's principles and their generalizations. That's what a classical physical theory is. So one of the really useful techniques in studying physical theories is to identify what kinds of symmetries the theory might have. For example, and this is one of the reasons that physicists often make a simplifying assumption to get an approximate situation that will have a lot of symmetry. So there's a very famous joke about what a physicist says when starting to discuss biology. The physicist says, consider a spherical cow. OK, so why consider a spherical cow? Well, you've got to have an object there. We've got to study this biological object. But it's too complicated to worry about the shape. So if you make it spherical, it's got this nice rotational symmetry. You can simplify your equations. We can spherical and we can write down equations for real cows, which are just small perturbations of the equation for the spherical cow. So we like symmetries, and we really like the power that symmetries gives us in solving the theories. And what Adler, Bell, and Joukiffe noticed in the late 1960s is that when you have a quantum theory and you look at the corresponding classical theory, the one that's more like Newton's laws, you might be able to identify a symmetry of the classical theory. For example, if you are doing Newtonian mechanics, doing the Newtonian mechanics, actually, let me not give an example because I don't want to get into the anomaly thing. But there can be symmetries of the classical theory which end up not being symmetries or having difficulty being symmetries of the corresponding quantum theory. And a lot of time was spent trying to learn how to determine whether a given symmetry really worked in the quantum theory or not. And the nice ordinary word anomaly was used to denote the kind of obstruction to the symmetry being the classical symmetry being a symmetry of the quantum theory. Well, what was learned in the 70s, in the mid-70s, is that the techniques which were eventually developed to explain these anomalies were completely parallel to work that was done by two mathematicians, very well-known mathematicians, Michael Atiyah and Isidore Singer, who had proved something called the Atiyah-Singer index theorem in the early 1960s. And that theorem relates analysis on a complicated space. So analysis means equations that have to do with differentiating things. Analysis on a complicated space to one of the space's topological properties, a particular one called K-theory. That's not really going to concern us, but I want to stress that the behavior in the index theorem depends on the shape of the space in which you're working. And in fact, that's one of the sources of potential anomalies in the physical theories. If you formulate the quantum theory on absolutely flat space, then the symmetry might work. But then it turns out that if you try to formulate it in a more general way where the space-time is allowed to have some deviation from flatness, you may not be able to bring the symmetry along with you. And that was related to this Atiyah-Singer index theorem. OK, I can't explain tonight the Atiyah-Singer index theorem or K-theory or any of that stuff. So I focused on the other example, which happened shortly afterwards. And the other example has to do with something known as Yang-Mills theory, which is a theoretical framework which studies interactions between subatomic particles. It had been developed in the 1950s by two physicists, C.N. Yang and Robert Mills, and it gained acceptance in the physics community in the late 1960s and early 1970s as providing the correct description of both the strong and weak nuclear forces. That's a slight oversimplification. I apologize to the physicists in the audience for having said it that way, but I think it's fair. Once it was kind of really firmly established by the early 1970s that this was the way to go, people wanted to study it in more detail. And one of the ways that was proposed to analyze it, which arose in the mid-1970s, was to study what are called the instantons of the theory, which I'm going to explain in the next several minutes. But the problem of actually, so it's one thing to formulate that you need these instantons, but the problem of actually finding the instantons required a team of mathematicians. This is a team of mathematicians which spanned the Iron Curtain at the time. So Drinfeld and Mani were in Moscow, Atiyah and Hitchin were in Oxford, maybe Cambridge, I think Oxford at that time. Atiyah flopped back and forth. It's hard to remember. But they were in communication with each other, and the four of them together found a very general solution to this problem that had been posed by some of their physics colleagues. Now, Atiyah's name is showing up for the second time. In fact, he had been involved in those discussions of anomalies and their relation to the Atiyah-Singer index theorem a year or two earlier, which made him sort of more aware and receptive to the ideas in physics, which were starting, again, to come into contact with mathematics in the mid-1970s. So, instantons. Instantons are a way of describing one of the key things that happens in quantum mechanics, which is called quantum tunneling. So I'm going to give a description of quantum tunneling in a minute involving sort of tunneling through walls, but that's not the only thing that can happen with quantum tunneling. Essentially, in quantum mechanics, as I mentioned before, there's a most likely thing, which happens most of the time, but then there's also an unlikely thing. So it may be, for example, that you're in a system, a physical system, in which you are trapped by your own energy level in this place that you are, and in order to get out of that place, somebody would have to give you a big kick. Like you might be on what used to be in the center of Aspen, that cool skate park thing, which is gone now. But you might be sort of rolling back and forth, not having quite enough energy to get up the lip of the skate park and over to the next part of the skate park. And what can happen in quantum mechanics is that all of a sudden you're over there. So that's the quantum tunneling process, that it was unlikely for you to penetrate the wall and get over there, but in fact, that's what happened. So here's a picture, thank you Wikipedia, which shows quantum tunneling. So I've got, in these quantum processes, I always represent things as waves. Most of the time, the wave will bounce back, and I'll be trapped to the left of my barrier. But once in a while, with an unlikely probability, I can actually somehow go through, even though there's a barrier there, I can go through, and the wave will continue. It used up some of the energy that the wave had in order to go through the barrier, so the height, the amplitude is a little lower on the right-hand side, but it can once in a while happen in quantum tunneling. Just to give us a little break, I just remind us from the news of other recent tunnels. There we go. So this was a tunnel in New York someplace, constructed by amateurs, as you may remember. This is the prison escape, if anybody doesn't know. I'm not going to show the whole thing. But indeed, it takes a lot of energy to get through the tunnel, and is very unlikely. That's the point I wanted to make from that slide. OK, gosh. Having done that, it won't respond to my... OK. How do I get to the next page now? There's a thing I can't see. That's not good. Sorry. Yeah. OK, we're going to have to do that 2 more times because full screen. All right, because I have 2 more videos. So instantons are this way of modeling the quantum tunneling effect, and they're actually, as mathematical solutions to equations, very closely related to standing waves. So it's a little hard for me to explain why the standing wave picture and the instanton picture are related to each other. One is called a soliton because it's sort of localized in space. The other is called an instanton because it's localized in time. And you've probably heard talks about special relativity where there's a basic equivalence between space and time. There's some differences, and you have to do something clever with the solutions to make this correspondence precise, but they're closely related to solitons, and so I wanted to give you an idea about solitons. So here's this really cool quote from the mid-19th century of the first time anybody observed a soliton of this kind. And this guy, John Scott Russell, was watching a boat being drawn along a canal, and the boat suddenly stopped, and the water that was trailing the boat kept going, and it kept going as a wave of water, and he decided to follow this on his horse, and it was going at 8 or 9 miles an hour and continuing at 30 feet long and 1 foot to 1.5 foot in height, and continued for several miles until he lost it in the windings of the channel, as he says. So this notion of a standing wave is an important way of thinking about these instantons. Here is a lady who's going to make an instanton in a water channel for us. Maybe if I let it run to the end, I'll be allowed to go to the next page. We'll find out. So here we go. And here comes the wave. No? Here comes the wave. Excellent. Now can I go to the next page? No. OK, that's not the next page. That's the previous page. There we go. It just won't go to the next page. OK. Sorry. So there's one more video. Here it is. Another wave. These waves used to be more common than they are now. OK, I've made a pun. Oops. Gosh. I made a pun about standing wave. But in fact, this is the same kind of disturbance of the medium that we saw in the water wave, right? It retains its speed, it retains its shape. People learn how to do it just by looking at the people next to them when they're supposed to stand up and sit down. And it's really an amazing, so long as people are paying attention, it's really a quite amazing phenomenon that it works so well. And here it comes back all the way over. It even skipped over that gap in the stands and continued on all the way around. So we got a whole circle there, and I've personally had enough of it. We can stop. Okay. So standing waves, and actually that's not a bad mnemonic to remember about standing waves. Oh shoot, there we go. So as I mentioned, Atiyah, Drinfeld, Hitchen, and Manin managed to find a solution to the problem of what are the Yang-Mills instantons. And in the spring of 1978, Atiyah came to the Harvard Physics Department to give what are called the Loeb Lectures, given every year, under the general title Geometry and Physics. These were his lecture titles. And the methods that he used, or that the four of them used, in order to produce these solutions, used a branch of mathematics known as algebraic geometry. And that branch of mathematics was almost entirely unknown to physicists at the time. It happens that although he was going to the Harvard Physics Department because there were people there very interested in these Yang-Mills instantons, the Harvard Math Department happened to have been a really excellent center of algebraic geometry, and I was a student in algebraic geometry at the time. So I was at these lectures. Ed Witten, who was a postdoc at Harvard, was also at the lectures. He and I did not meet for many years thereafter, but we subsequently compared notes and learned that we were both there. And it was a really exciting event for both the mathematicians and the physicists. Physicists because they had some new techniques to learn and solutions to a problem that had been around that they had regarded as a very difficult problem. Mathematicians because, gosh, we were studying these very abstract areas of mathematics, algebraic geometry, and all of a sudden it was being applied to theoretical physics in ways that nobody had imagined could possibly happen. And I wrote this was the largest such gathering in many decades. In fact, it seems to me that it may have been the largest such gathering ever at that time, simply because the number of people working in those fields decades before the divorce was much smaller. So even if they had all gotten together back in the 20s and 30s, there might have been fewer of them than we had in those 4 lectures of Atiyah in the spring of '78. Okay, so I brought back the Feynman quote one more time, and I highlighted this time the description of topology. So this was exactly the sort of thing that Feynman found so distasteful when he understood what was being taught to the mathematicians who were friends of his in graduate school. But topology is, as Gleich says, the study of shapes in 2, 3, or many dimensions without regard to rigid lengths or angles. So that field of topology is something which was developed starting in the early 20th century. Princeton in the 30s and 40s was a real center of topology, which is why that's a really good example from Feynman having been a physics graduate student at Princeton in those days. The subsequent developments that I want to discuss now that happened after this lecture that Atiyah gave, I've titled the slide, Physics Leads to Mathematics Leads to Physics Leads to Mathematics. We really had gotten something going again at this point. So that problem of finding the instantons in Yang-Mills theory, the one that Atiyah and his collaborators solved, led within 5 years to some really remarkable advances in mathematics. So there's a guy named Simon Donaldson who was a student of Atiyah, actually became a student of Atiyah after this time, and he used the theory of Yang-Mills instantons to analyze the topology of 4-dimensional shapes. So what Donaldson showed was that in 4 dimensions, there are restrictions on which shapes can actually be described smoothly, which I've just sort of indicated as without jagged edges. That doesn't really convey quite enough of the idea. But around the same time, there was some work of another mathematician, Michael Friedman, who was working on the shapes without any assumptions of smoothness. And Friedman's results diverge from Donaldson's in a way that lets the pair of results imply that there are 4-dimensional shapes which only exist in jagged rather than smooth form. And this was really a surprise. People had shown in dimensions bigger than 4 and also in dimensions 2 and 3 that all shapes could, sorry, the three-dimensional result wasn't quite proven yet, but people had a good idea of what it was supposed to be, that shapes all existed in some kind of smooth form, and that just stops being true in dimension 4. So how did we get from these Yang-Mills instantons to topology? Well, as Einstein's theory of special relativity first taught us, we're really living in a four-dimensional space-time. Space and time are together. And those Yang-Mills instantons had to be solutions in a four-dimensional context. And so there was a new tool to produce some kind of interesting solutions. And those solutions have something to do with the shape of the space. And you can see that by the structure of those standing waves that we had a few minutes ago. You can imagine that if the space turned one way or the other, the behavior of those standing waves might somehow reflect the underlying structure of the space. And that's indeed the basic idea behind Donaldson's study of instantons in analyzing the topology. So that study really only applied when the space could be described smoothly. Donaldson found that there were restrictions on such spaces, but Friedman found that there were very few restrictions on the shapes themselves. And so that's why we end up with this conclusion that some shapes are only in jagged form. OK, next iteration of this sequence. Donaldson's work inspired a physicist named Edward Witten to formulate what are known as topological quantum field theories. So Donaldson had been inspired by these Yang-Mills solutions, but the way he used them was not the same way they were used in physics. And Witten, when studying this, realized that there was an interesting modification you could make of a quantum field theory, which combined it with some aspects of topology. And sorry for the typo, these topological quantum field theories have found applications in a very wide variety of settings. I'll just mention Michael Friedman one more time. So Michael Friedman, who, by the way, Friedman, Donaldson, Atiyah, Witten all won the Fields Medal in mathematics, which is sort of like the Nobel Prize of mathematics. So the accomplishments, well, Witten's Fields Medal is not for this particular accomplishment, but these are top-class people in the field. Witten is the only person with, I believe, with a physics PhD to have won that mathematics prize. But Friedman went on, and in the last 15 years or so, has been leading an effort at Microsoft Research to develop quantum computers based on ideas derived from this topological quantum field theory. And there's a picture of the group of researchers. They're actually based on the UC Santa Barbara campus, although they're a unit of Microsoft Research. So it may be that that idea actually produces quantum computers in the not-too-distant future, even though it came out of this very strange sequence. So I'm not done with my sequence. So the Donaldson results were early 1980s. By 1994, there was an additional advance made in the study of at least a certain class of these Yang-Mills theories, Witten in collaboration with another physicist, Nathan Seiberg. And they found that, in certain cases, the same information carried by the Yang-Mills instantons could be reformulated as information carried by solutions to a different set of equations, which are called the Seiberg-Witten monopole equations. So I correctly predicted I wouldn't really have enough time to talk in detail about monopoles. Monopoles are another interesting topic in theoretical physics. If you have a magnet, it has a north pole and a south pole. And if you break the magnet in half, you end up with two magnets, each with a north pole and a south pole. And the idea of monopoles is that maybe someplace there is something that only is a north pole or only is a south pole without having the paired part of the magnet. And that's a theoretical possibility which is allowed by Maxwell's equations of electromagnetism but hasn't been observed in nature. But monopoles, even though it hasn't been observed in nature, people don't dismiss it right away because it's a natural feature of the equations. And for example, people who think about what happened in the very, 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 very early universe worry about monopoles probably formed and how did they go away? Why don't we see them anymore? So monopoles in many contexts are interesting topics in theoretical physics. And it turns out that there's a way of kind of rewriting the equations so that the essential information could be found by solving a different set of equations, the Seiberg-Witten monopole equations. And those equations turned out to be a lot easier to solve than the Yang-Mills instanton equation. And so as a result, we had immediate implications back in topology. Donaldson, which was really based on Yang-Mills instantons in some form, had led to a detailed understanding of topology in 4 dimensions, but it raised lots of new questions, and it didn't answer all the old questions. So this theory of 4-dimensional topology was a very active one at the time of the Seiberg-Witten work in 1994. And all of a sudden, the practitioners had a brand new tool, these new equations which were actually easier to solve than the Yang-Mills equations themselves. And many long-standing questions were answered and long-standing conjectures settled within the space of a few weeks to a few months after Seiberg and Witten announced their work. In fact, people did things like compare emails and what time the email had been sent to sort of argue about who had proven the result first, things of that sort. OK, so the last thing I'll say in closing, and Timo, without knowing the slide was here, already alluded to it a little bit. I want to explain why I'm in Aspen this month. So I'm here at a workshop on something called F-theory and its applications to particle physics. And the background for me is a very different one than what Feynman experienced. So it's true that the theoretical physicists and the mathematicians are still largely pursuing independent courses of study, but there are many places of overlap, and there are many people who go out of their way to learn pieces of the other subject in order to be able to engage in this collaboration that we have ongoing. So because many modern mathematical tools, such as topology or index theory, are indispensable for theoretical physics, you find physics students taking math classes. Because there are many parts of mathematics that have benefited so much, such as 4-dimensional topology, from the ideas imported from physics, you find lots of math students taking the basic physics courses to find out how those ideas happen. A notable example of the collaboration is string theory, which, if you come to these lectures with any frequency, you hear about from time to time. Many, many ideas from modern mathematics were required during the period in which string theory experienced explosive development from the mid-1980s through the 1990s. And conversely, ideas from string theory stimulated a lot of mathematical advances. For me, there was a turning point. So I was trained as an algebraic geometer. I was very interested in those Loeb lectures of Atiyah. I learned a little bit about the twistor space methods that they used, and I didn't pursue that as a research topic. I didn't really know too much about what was going on. In 1984, when string theory really got going, I again talked to some physicists, learned a little bit about it. But the turning point really came in 1990 to 91, when physicists found a new way. OK, it sounds a little esoteric. They found a way to count certain two spheres lying on a particular 6-dimensional shape, known as a Calabi-Yau threefold. That sounds a little esoteric, but those 6-dimensional shapes happen to be ones that I was studying already for other reasons. Having a new way to count things is OK, but what was really striking about this was that their method was to do a different calculation, not a counting calculation, but a calculus calculation on a different Calabi-Yau threefold. And that was really surprising, and it led me to start collaborating with physicists, trying to find out what was going on, to understand things better, and that's what I've been doing since the early 1990s. So this month in Aspen, we're looking at a variant of string theory, which is known as F-theory. Its formulation and the calculations that you do with the formulation involve some very sophisticated mathematics. On the other hand, the models that we're producing seem to be very promising as potential descriptions of our world at higher energies than we're currently observing in the laboratory. What we would like to do is bring it down to the energies that they're seeing at the LHC, or maybe the LHC's successor. We're some distance from being able to do that in a quantitative way, but the qualitative features of a number of the models are very promising. And the workshop that we're having here this month actually spills over into September, involves people from both ends of the spectrum, several whose PhDs are in mathematics rather than physics, including myself, and then others who are much more closely involved with the modeling of particle physics. And we're making a lot of progress together. So I thank you for your attention. Any questions? Yes, sir.
I'm just curious. I just read an article about some results they're getting from the Antarctic neutrino detection system, and the neutrinos that they believe they're seeing, they said have much higher, extraordinarily higher energy than can be generated at the LHC. I'm just curious if your F theory is dovetailing.
So the question has to do with neutrinos being observed at the South Pole, which are at higher energy scales than are currently observed at the LHC. We can learn a lot of things by making observations of the world around us and by finding situations where there's a lot of energy involved, but we don't have any way to control what's happening there. All we can do is look to see some process that happened at that energy scale.
The mathematics of your F theory dovetail with that.
What I'm trying to say is that if we wanted to test a particular result, we would like to tune the parameters of what's happening at those high energies instead of simply observing what might have happened to neutrinos at those same energies. So we're not going to learn as much. We might still be able to learn something. We might get some evidence for one of these theories, but we won't be able to give it the kind of definitive test that a laboratory experiment would enable us to give. Now, one of the criticisms leveled against string theory often is that it's not making testable predictions. And I alluded to that in my statement that we have better qualitative than quantitative results at the moment. The thing that, well, I don't really want to get into LHC physics too much, but the thing that has frustrated people with the data that's so far come from the LHC is that they were all hoping to see something brand new other than the Higgs. So the Higgs was great, and we're all very happy that the Higgs was observed, but they were hoping to see something else brand new, and they haven't seen it yet. But LHC has started up again at higher energies, and so we're hopeful that there will be some new physics, and that new physics is what we'll be trying to explain. Yes?
When you're talking about 4 dimensions or 6 dimensions, is that 3 or 5 plus time, or are they all spatial dimensions?
So the question is whether my 4-dimensional spaces are all 3 plus 1, or my 6-dimensional spaces are all 5 plus 1. And the answer is that I can study both kinds of spaces, either ones which are behaving purely spatially, or ones which have both a space and a time component. So let me explain briefly where those 6-dimensional spaces came from and how they're related. One of the odd features of string theory, which many of you will have heard before, is that it naturally predicts a theory with 9 space and 1 time dimension. And the way that we get down to 3 space and 1 time dimension is to look for models in which 6 of those spatial dimensions are very small, and the properties of those dimensions then govern the physics that we see in the 3 plus 1 dimensions around us. It's a little esoteric concept, but that's why a 6 purely spatial dimensional object is pretty interesting in string theory, and that's why the string theorists were looking at those objects. Yes, sir?
It seems that Stephen Hawking has some new ideas on black holes and the preservation of information paradox. Was that a mathematical insight on his part, or did mathematics play some known role in his new thinking about the information paradox?
So the question is about Stephen Hawking's recent revisionist thinking about the black hole information paradox question and whether that's related to mathematics. The black hole information loss paradox is something that's been discussed a lot with many different tools and ideas, all of which are pretty mathematical. There hasn't been an occasion to invoke a theorem like this Atiyah-Singer index theorem that I mentioned, or Donaldson's work on 4 manifolds, some existing sophisticated mathematical tool to apply to that problem. But they have used a lot of interesting mathematics along the way. There have been a number of really interesting developments recently. One of them is some connection with the theory of computing. So people who look at computers and how they behave have developed various kinds of theories of computing, and that may have some tie-in to this information loss question. I have only read press accounts of Hawking's revision in his thinking, so I don't know the details of what has led him to that. I haven't had a chance to study it in detail myself. Yes, sir?
There's a little information. I happen to have one of the releases. It's from The Economist, and this is specifically what it says. His inspiration came when listening to a lecture in April about what are called super translations, a bit of heady branch of mathematics known as group theory. So the answer to his question is yes.
It involves group theory. Great. So the question was answered from the audience. Further questions? Yes, sir.
Could you say a little more about the instanton? The soliton has a lot of observation, water waves, most any type of wave. You showed what I thought the crowd's parent motion through the stands at one point. But could you say a little more on physical manifestation of the instanton?
So the soliton is supposed to be localized in space, and the instanton should be localized in time. So if I'm treating my 4 coordinates, 3 spatial and 1 time, on a democratic footing, then I can kind of rotate the soliton solution and treat one of the spatial coordinates as a time coordinate and get something like an instanton solution. Now that's an oversimplification. I have to use something called Wick rotation in the process of doing this, but that's roughly the connection between the 2 ideas. More questions? Thank you again.
Thank you.